Hi, hello, good afternoon. Thank you for joining, especially if you're coming from Poland, where we officially start the holidays. So thank you for using this time for being with us. Though we know that for some teachers it's still the teaching period. So still, thank you to all of you. Okay, not to punish those of you who are present, I would hello. Uh, Yes, so not to punish those of you who are on time, I would start promptly. And as I see that mainly we have the participants who already joined the previous meetings, I can then skip the introduction because you already know that we are here as a STEAM4Climate consortium and that we are now dealing with the teacher training. And I hope you are familiar with the handbook we created for you for teachers. And especially today, I'm going to once again refer to this idea of low floor, high ceiling, wide walls. So if you read this pedagogical concept, today I'm going to provide you detailed examples how to apply this within our teaching. To remind you that we have these 5 projects running. Today the meeting is dedicated to the last one, the 5th one, about the STEAM way of doing of studying ecosystems. Just a reminder, we have those activities in the handbook. But now moving directly to the today's topic. I coined the term I gave the title From Measurements to Meaning. And that's exactly what we're going to do today. Do some measurements and try to interpret them to understand what is happening inside the biological systems. Because I can say something that is absolutely obvious, that we all know, for example, that organisms breathe. And like every child knows that we take in oxygen and release CO2. And if you happen to have a garden with a compost, you notice, especially during the winter, that it's very warm. So we see that during the decomposition by microorganisms, there is a release of heat. And anyone who spent a moment in kitchen knows that yeast needs sugar to thrive, and that they also release CO2. And this is why if you at least once did with your own hands bread or pizza, then you know that yeast needs sugar, and they produce some gas. But the question that is here rhetorical is if you have ever measured it. And that's the whole motivation behind this scenario. That personally, as a physicist, I spent a lot of time doing practical exercises in physics when I was in high school, and I'm doing this as well with my students. But honestly speaking, there was maybe not none, but very little practical experiments or approach when it comes to to my biology. Hopefully, it's not your case. I hope in your country or in your high school you get better education. But when I keep asking people around in different countries, the picture unfortunately was rather consistent, that even if there are practicals in bio, there are rather qualitative, and in first place they're rather about ecosystems or biochemistry, but there is no like interception with ICT. So what I want to show you can look a bit complicated, but I think you all already know that part. That again, we have this theoretical knowledge that there is the thing called photosynthesis, where there is the uptake of CO2 and production of oxygen. But now, could we really observe it? Yes, just if we can detect CO2 or detect oxygen quantitatively, then we should see day-night cycles. Can we? We know that every living organism is needs respiration, so we know that everything produces CO2. So even if it's not a plant, it can be yeast, it can be bacteria, it can be fungi, it can be anything. Every living system is going to emit CO2. So can we study this in aerobic and non-aerobic conditions? Yeah, if we have CO2 detector. We know, and especially in Poland, because we just on Friday we ended the school year, then a lot of parents kept reminding the old meme that the most important thing now is to remind a child to take the sandwiches from their bag, because they'll be conscious after 2 months spent there. So we all know that there is the thing called decomposition. We all saw mold, we saw rotten food, but is it possible to check what is exactly happening there? Yes, if we can measure emission of CO2, which is emitted during decomposition, or NH3, which is and CH4, that are also emitted during the breakdown of the complicated proteins, and so on and so on and so on. So we all know those concepts from biology, but again, my honest question is, how many of you have ever checked if this is really true, what our teachers in high school told us? And same goes for not only for biological systems, but when it comes to environmental science and chemical science, there is also a lot of concepts that builds to this wider knowledge about the climate or the environment, and the things like carbon cycle. Again, in every book about the climate, there are those arrows showing how the carbon cycles around the Earth, around the ecosystems. But again, anyone measure this in high school? I really doubt it. But fortunately, what we did within this project, we decided to go through retailers to find the equipment that would be suitable for the high school measurements that could enable us to measure environmental conditions, including CO2, but in an affordable way. So we are very happy to to find out that there is a piece that costs around like 70 euro, but it's worth the price, because that thing that again, I'm going to show you today a few times, that tiny piece contains a detector which is called photoacoustic spectroscopy. So it's something that was definitely you haven't had it when you were in high school, because this is a concept that was invented a few years ago. I mean, not more than a decade, I think. And the whole idea is that inside this small cube, there is a really tiny microphone, and there is as tiny emitter on infrared light. And as you know that the CO2 is greenhouse gas, which means it captures infrared. then it means that if there are molecules of CO2 inside that chamber, when they absorb a bit of that infrared, then they are going to vibrate a bit, a bit. But this a bit creates enough pressure for this tiny microphone to measure it. So it's almost unbelievable, but it really works. So this photo acoustic spectroscopy works, and thanks to those MEMS technology, when we have microelectronical mechanical systems, with those two elements, we can simply measure the voltage on the microphone, which can be correlated to CO2 concentrations. And again, because the air is not absorbing infrared, then this is specifically measuring CO2. Okay, but even if we found this this beautiful piece of electronics that does not require you to spend like money for the scientific grade equipment. Still, there are a lot of problems if we want to push it into the classroom. We acknowledge that not everyone is a programmer, not everyone is excelling in Arduino kind of projects, but still we want to gather some data, and if you want to run some experiments that will last for example for a days, would be really nice to keep track of time, so would be nice to have a real-time clock module, and of course would be nice to have a place where we can store the data so we can later access it, but meanwhile would be also nice to simply see what's happening, to do, for example, some tests, or even to gather the data manually. And fortunately, instead of building a bigger and bigger, let's say, Arduino-based system, um, after the multiple tests we ran, we found this piece called data acquisition module, science data acquisition module. So the whole idea is now that you don't need to have any programming skills, because this module will take the whole workload from you, so you can focus on the most interesting thing, so the doing the measurements in and interpreting those measurements. So basically how it works, and 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 this is the thing I'm holding in my hand. So you see it fits to the human palm. Okay, so what we have inside. As you see, we have screen, so we can immediately see the readings. We have button that can control the settings if we wish to, and there are inputs for different sensors. And now, what is super interesting in the system that we found and we chose is that maybe you notice that that piece comes from the gravity ecosystem as well as that one. So someone clever decided that that piece will have all the addresses of different sensors already embedded in this memory. So the only thing you really need to do is to plug your detector or your sensor to the input port. And that's it, because that microcomputer will recognize address of that sensor. So when reading the data from that sensor, it will automatically display appropriate values with appropriate units. Now, if you wish, you can now as always, you can complicate more. So you can use the output to send the data, for example, to Arduino or to whatever you want. You can connect Wi-Fi module, or you can connect a wire and through USB connect to the computer. And you can build as complicated station as you wish to. But as long as you're using the gravity sensors, then that's all you need to do is just plug and play. So here there is this concept of low floor. So you don't need to have to be a high tier student. Even the students who are struggling shouldn't struggle here when actually you need to connect sensor to the logger and provide the power. So that's the idea of low floor. You can easily start with basic tools and no prior coding or electronic experience is required if you're using that kind of kit. But now, as you can imagine, of course, there is high ceiling there because one doesn't need to just use CO2 sensor. We can connect here whatever we want. I'll give you examples in a second. But this gives you like a platform that is easy to start and then gives you ability to build bigger and bigger measuring systems for top tier students. And what I'd like to stress is that there is also this white walls approach. So after some basic introduction that I'm going to show you today, then it's up to you. It's really open. What's the next step? So we can do completely different experiments in completely different ecosystems if you wish, and all of this will build into this idea of measuring what's happening in the environment. So the thing that I'm holding here is the version that is a bit more complicated. During tests we wanted to measure as many things as possible, but in this section, in the next half an hour, I'll just focus on this low floor. So just I have one CO2 sensor, a battery, and the data logger. Okay. If there are any questions, you can use this Q&A button up there or leave the comment on the chat, or you can simply leave it till the end. But now let's check if the equipment is working. I'm sorry, I need to get rid of the background for this. None. Right. Okay. So once again, what you see here from scratch. This is the piece. The only thing I did before when it came to me, I plugged here the tiny battery that was in the set. So even now when the power is disconnected, still the real-time clock is working. So now when I connect it, you see the time is still right. And the device that is connected here, you see here. Okay. Immediately, because I connected this through USB, which is connected to my computer, already you see that, oh, we have some data gathered during the tests. That's right. But how this happened? Here, you can click set, and I'm not sure if this is readable. I'm afraid the resolution is not perfect here, but just briefly, if you click set, you can set the time. That's the first thing. Secondly, you can set the refresh rate. So you can decide if you are measuring, for example, every second, or if you are measuring every minute, or if you're doing long-term experiment and you're going to measure, for example, every hour for a few weeks. So it's up to you to decide. When you decide and you click rec, record, you see that now this blinking diode indicates that now data is stored. And now yeah, it's hard to read, okay, but yes, now I see 680 ppms. So this is the amount of CO2 which is now here. And as I close windows, not to have noise from the outside, and I'm talking and I'm breathing towards the sensor, you can see the value is rising. Oh, if you can see it actually, let me stop the recording. I need just to reset the connection, and let's check. Uh, um, And let's check. Oh yeah, we have data here. So if we just uh, open Excel and import that file here, then then that's it. You see time and you see CO concentration. You can make a plot. I think that's the moment when I turned it and started breathing into it. So there was this change. So okay, this is working, and already there is the value in it that you can check what the ppm means. So you can check what's the value of CO2 concentration inside the office, inside the classroom, inside when the lesson starts and when the lesson ends. And as well, you can go outside, so you can build the basic understanding if, for example, 500 or 5,000 is a lot, or what exactly. So that's the first thing. But then, if you remember the very basic experiment that is done in the primary schools just for a show, now we can do the same experiment, but this time not just as a show. Look what I mean. What I have here is the baking soda. It can be pure baking soda, or it can be um, uh, I mean, you can have the chemical ingredient, or you can take it simply from the kitchen. And if you have any kind of container, for example, I'm using regular jars. And again, now I'm doing this a bit clumsy, but imagine that I have my pocket scale and I'm using a very specific amount of the ingredients, which I'm not doing this very precisely now. Um, so now, if you just add citric acid, which I got here, and it disappeared. Okay, let's start with a bit of water. Again, in the student guide, you have exact calculation how many moles of citric acid and how many moles of baking soda you should add to have the best result. But here, you see, I'm doing this like more or less, so it will work. Okay, let's admit our colleagues. Give me just a second as my citric acid disappeared. Yeah, okay. And I have citric acid, and And now I click recording, and I'm putting this inside and leaving. So you see, that's the idea, that now our detector is measuring CO2 inside the jar, while you can see the bubbles, so CO2 escaping from this mixture. Let's give it a moment. I can already see 23,000. So it's a lot. 29, 32. So you see already in this chemical reaction, yeah, we don't need to wait long. Okay, my bad, I didn't click recording. Okay, so it's not blinking, but fortunately, I have the plot taken from the previous trial when I got exactly the values that were fine. And if you look into the time scale, this is very fast experiment, because within seconds you can reach up to dozens of thousands of ppms. Probably saturating the detector if you're using more than a few grams. So this was like a 5 grams of baking soda, which means it's very affordable experiment with really like a 2 grams. And you can check how mixing or how temperature of water influences the outcome. Okay, so I see 39,000, so it's reaching the maximum value for that detector. Okay, so if we can do this, so if we can measure CO2 concentration, then let's do something that is not exactly a chemical experiment, but I mean, it's still chemical. But now we want to check what's happening when we have something that is alive. And so again, I assume you know from the primary school this experiment where you put yeast, sugar and water into a bottle, and you seal it with the balloon, and after some time you see that the balloon is expanding. So again, this is qualitative observation that, yeah, there is a release of some gas, but now if you do exactly the same, but instead of balloon you use a jar and put inside a CO2 detector, you can see exactly how fast is this production of CO2. And now in this case, I will skip the experimental part for the one reason that it takes like 40 minutes to like fully show what's happening. Um, so I encourage you to do this on your own. And you see the classroom, one period is enough to obtain these very nice results. So if you do what I just did, so record and then create a plot, then you see what is the concentration of CO2 over time. And the box is sealed, so it's definitely going from inside. And what fascinated me as a physicist is that those yeasts behave like just like a weight on a spring. I mean, it was repetitive. It was uh, clear. There was not even a lot of noise in this data. It was like a pure straight line. It was a constant production after some initial phase when those dry yeast that I used like woke up and start eating sugar. And from the gradient, you see it was 315 ppms per minute produced. And what's interesting about this, that again, this is not surprising to anyone, and definitely not for a biologist, that there is a production. But to the biologists that I show it, it was also impressive that you can quantify what is exactly happening. And you can imagine now what's going to be next step, right? So give it a moment. Just one more slide. That when I left it unattended for overnight, for dozens of hours, what I saw that this gradient finally was lower and become flat. So what actually happened? Or maybe anyone on chat want to share their idea. Though I know it's late and some of you are already on the holidays, so I don't want to press you. Yeah, but what happened here is that we ran out of the sugar. So with the 5 grams of sugar that I used, it's simply they ate it and then again become dormant. So there was this plateau in the end. But when I again add a bit of sugar, I mean a solution of sugar in water, again I got the production, or rather the outcome of their metabolism. So one can do a simple experiment when with a syringe we can add and add and add from time to time known concentration of sugar, and we can see how they are consuming it. And by the way, here disclaimer, I'm not a biologist, so I just noticed that the shape of the curve seems similar to the microorganism growth. I'm not sure if this comparison is right, but here I admit I'm also open to discussion, and as a teacher I don't need to know everything. Now I can do the inquiry with the students, so we can together check if this is just a correlation, or they can go and ask bio teacher, or they can be better at biology than me, and but we can do it in this open way. We have here white walls in this approach. Okay, so if we can do this, we can see how the what is the fuel consumption, the rate of the fuel consumption. And now we can do the next experiment, still using in this case yeast. We can check what influences the rate of their metabolism. So I already mentioned one thing, that yeah, the amount of sugar would be one thing, but I told you that I added 5 grams of sugar. And by the way, the regular sugar, cane sugar from kitchen, it doesn't have to be glucose or whatever pure, just like doing pizza, just regular sugar. So what happened? Um, what if I use, instead of 5 grams of sugar in 100 milliliters of water, what if the concentration is different? What if still the amount of sugar is the same, but it's more or less concentrated? I don't have slide for that one, but I know someone did it and check that there is the maximum value when simply the concentration is too high, and yeast cannot live in such big concentration, because they are drying out. So you see, again, we are going into like depending on the interest of the class, we can study maybe this, or maybe this, or maybe this. What I did with the teachers who are present in my teacher training, we use different temperatures of water. And again, I think we all know that the temperature is important to biological systems. We all got fever from time to time. We had those stories that for some organism, particular temperature means death, particular temperature means hibernation, and particular temperature means that they are thriving at this in this moment. But I was again surprised uh, how big is this difference, and how precisely we can quantify this difference. So what I showed you before was the experiment when I used tap water with the 20, around 17 to 20 Celsius degree. And there was this concentration. You see, after 40 minutes, we reached 10,000. So the production was around 300 something ppms per minute. Now, when we used, someone boiled the water and used 37-degree water, which is optimal for yeast, then we got 6,700 ppms per minute, which means we increase the activity of those yeast over 20 times. Because again, we use the same mass of yeast, the same amount of sugar and the same amount of water. The only thing that changed was the temperature, and we got the 20 times higher metabolism, just because of the changing temperature. You can imagine now that having the whole class with jar per pair, for example, we can repeat this going, for example, every 5 or 10 degrees, and do such plot for 10 or 10, 20, 30, 40, 50, 60, and check, reproduce the curve that we gain know just from the I assume from the textbook, where we see that above certain temperature they are dying, because below the certain temperature they are dormant, but there is this peak value when they are super active. So this brings us to quite wide conclusion. Now, because if we get this concept that activity of some enzymes is heavily influenced by temperature, and therefore activity or the efficiency of different microorganisms is also influenced by temperature, then the headline like this makes sense, because now we get it that, right, if it's getting warmer and warmer, it means it's not only warmer for us, but it's warmer for the whole environment, including soil, and including bacteria living in soil or living around us. So what happened in Kazakhstan a few years ago was mysterious death of 200,000 saiga antelopes because of the previously not dangerous bacterium. So they were infected while simply because of the higher temperature, the bacteria that was in soil uh, got activated, released, and got super contagious, and did this like mass death around the whole Kazakhstan, causing a huge damage to the economy in the Kazakhstan. So you see the linkage between what's happening in the very simple experiment in laboratory and the wider interpretation of what's happening in our environment. So very sad story, but showing simply the dark side of what's happening in different regions of the world. Okay, but speaking of soil, um, what if we have not necessarily beautiful plants or those domesticated yeast, but simply a piece of dirty soil taken from the garden. That one is really dirty because it's here for like 2 months. But what I'm going to show you is a graph that again can be a bit complicated because I put all the measurements at once there. But I hope you see that, yeah, this is exactly the same jar while it was clean. So with the fresh soil taken from the garden, what I did, I added again 5 grams of sugar with some amount of water, and that's it. And pour it inside. And then what I noticed that again, okay, when this dissolved sugar reach deep into the soil, then the CO2 production skyrocketed. So something inside and then spoiler, bacteria living in soil, they keep consuming that sugar and releasing CO2. Meanwhile, if you participated in the first meeting with Thomas from Kepler-Gymnasium Pforzheim, he discussed the topic of the wet bulb temperature, and he brought this concept that the relative temperature, so like, or how it feels, how warm it is, depends also on the humidity. And what was the reason? That we are cooling ourselves by evaporation. So look what you see in this green graph, that when the detector was just beneath the lid, so initially there was some like 40% of the humidity, just like in the air outside. But when the system was closed, then the water that was in the soil kept evaporating. But evaporating for how long? Till the humidity reached around 100%, 95 to 100%, and the water keeps condensing inside, which you can see because there are droplets of water on the sides. So you see that now we have the closed cycle, so the water that is condensing, the amount of the water condensing and the amount of the water evaporating is the same. The rate is the same, so the humidity is not changing anymore. So the moisture of soil is the same, because there is a balance between soil moisture and air humidity. And the last thing, you see the drop of the temperature because I put the water, which was relatively colder than the soil I've taken, but then it was pretty stable. The only thing that changed here, if you correlate this with the notes, what happened when, it was simply the moment when it was standing on the near the window while there was the sun shining. So we see here a bit of greenhouse effect inside. Now, you see, I said a lot of things about this one simple graph. You can imagine that, by the way, I spent hours on making this graph and playing with it, but you see what I want to say, hopefully, that this is the meaning that we can take from the measurements. And I can imagine students redoing this process, so trying to understand what happened actually here, what happened here, and they can do it if they do additional experimentation, or if they check their logbooks to check what event made this possible. I have one acknowledgement that the idea of measuring the soil came from I found it on the DF robot community, so the producer of the item we are using. Though what they did, they additionally used also the NH3 detector. So they measured not CO2. I mean, I think they measured finally both. So you see here ammonia concentration, and again, when you have different pieces of soil, and you have like a regular soil, and you have soil which is mixed with fertilizer, then you can see what's the difference in ammonia release, and you can start the discussion about over-fertilization of, of the environment. Now for something a bit different, but still within the idea of um, answering questions not by intuition but by measurements. I confess I'm not a good gardener when it comes to keeping care of the plants at home, and my mother kept telling me that I should water ficus that is in my room, but I didn't know when and how much. So when we started realizing this project and I got a lot of equipment, I simply use it as well to measure the moisture level of the soil in this. And by the way, yeah, it's that one. Yeah, that's. So it's still alive. It's the best advertise that it's working. So the point is that here, when you measure the temperature of the soil, you measure electrical conductivity of the soil, and you measure moisture of the soil, you have the qualitative information of what's happening inside some biological system, which is a great starting point to introduce to students the idea of smart farming. When modern farming has nothing to do, or not much to do, with what we see on medieval paintings, with people using their force to you know how mundane and hard agriculture can be. Now we have rather drones observing the soil. We have cameras with artificial intelligence studying of what's happening and looking for insects. And we have satellites on the orbit measuring by use of microwave radiation the soil moisture of the ground down there on Earth. We have a lot of high technology used by agriculture people bringing food to us. So to bring this concept, how they do it, there is a simple idea. Let's check how often you should measure, how often you should water your plant. Because if you can do this, if you can keep this one plant at your home, then there is a chance you will get the idea of how to build a bigger system. So again, if we have just the soil moisture over time, what we need to do is to assess the rate of loss of the soil moisture. So if you Googled or if you ask biologists or anyone that knows what should be the moisture for that particular plant, then that's the first piece of information. Then you qualitatively from the rate of change, the gradient of that plot, you can measure how much percent points you're losing per day. So to give you insight, what I did lately in May and June, there was a long period when, yeah, I was not watering my plant. And simply from the difference, we are providing simple a worksheet so students can calculate it. Having this data, they can calculate what is the moisture loss. So I know that my plant is losing 1.2 percent point per day. Now, when I was watering with like one jar, so every time with one or with 3 liters of water, I can assess what's the change, so what's the increase of the soil moisture when I'm watering with 3 jars. So you see, if I know before and after watering, so I see what's the moisture increase. So if I use 3 jars, then I see that 1 liter jar for my pot gives me increase of 7.5 increase of moisture per day. So now if I know that I'm losing 1.2 per day, and I know that 1 jar gives me 6.5, then by just 7.5, then by dividing those numbers, I see that I need to put 1 jar 1 liter of water every 6.5 days to keep the level of moisture the same. So again, simple calculation, but giving a good insight of what's happening there. And by the way, you can of course ask if this moisture loss is constant or if it's changing, for example, with the temperature or other conditions. Because the plant is inside, indoors, then the gradient here is almost the same, regardless of the temperature outside. But of course, if you're doing this outside, then you need to account for this. So you can add the next level, go from the classroom to the school garden, and there do the advanced project. Okay, but maybe you notice that I have a plot not only showing the soil moisture, but also electrical conductivity. So it matters what kind of water we are adding to the plant. Um, so is it distilled water, which gives moisture, but not necessarily electrical conductivity, or like during the workshop, uh, someone took the carbonated water and put it to my plant, and then I saw a spike with the huge electrical conductivity. So again, here you see step by step we are building more complicated concept that actually it's not just one parameter you need to keep in mind, but now depending on the kind of plant you have, you need to also maintain a particular electrical conductivity, so particular salinity. That brings us to the concept, is it really good to use the gray water? So to save water, to recycle the water, so the gray water is the one, for example, coming when we are washing hands. So it's the water we are not going to drink because it's already with huge concentration of ions coming, in this case, from the soap. But still, it's a high quality water, not drinkable, but high quality water. So we can, for example, water our plants. Now, yes, we can, but there is a question: which plant species are resistant to very high levels of salinity, and simply you can adapt your garden to the kind of water you're using to water it, or the opposite, maybe you need to desalinate this water before you add it to the system. Again, look, I'm not giving here like exact way how you should do it. It's like building a concept, and then with the students' interest, you can follow if we want to do it inside, outside, with this version of this version. By the way, I see Renata mentioned pH previously. Of course, this is also important. What about the pH of that water, and so on, and so on, and so on. So we can infinitely complicate and go into details. But getting back to the simple concept, if we get back to the very simple question, why we need to water those plants, then there is interesting question: is it because there is an evaporation from the soil? Not necessarily. Rather, because we have transpiration. So there is a water escaping from the plants, creating sub-pressure to suck the water from the roots. Again, concept from the primary school. But again, I confess, I've never had the opportunity to measure the transpiration, though before that project. But within this project, I learned that there is the device called potometer, that is a simply a tube where there is a scale with a bubble moving. So if we put the piece of a sprout or leaf or any piece of the plant inside, it's sucking the water through the tube. So in this capillary tube, we see bubble moving, and we can assess how many milliliters per minute it's draining just through transpiration. And again, of course, now if you use more light or a different temperature, we can check how the uptake of water changes when you change the external conditions, which again, it's important to understand how as well the photosynthesis works, and so on and so on and so on. So this is a relatively cheap device that, again, if you if you buy a capillary tube, you can build one on your own. But again, building to this concept of measuring what's happening inside the environment. And slightly going to the end, there is the question, what next? Because what I showed you is like just an introduction that we can measure things. Now, to add one discussion, what's the goal here? So the first goal, the let's say philosophical or conceptual goal, is to understand how important is biodiversity, because when we see, for example, the carbon cycle, we see that something produces CO2, but then something consumes CO2. We see, again, we don't read it, we see it in the jar that to absorb CO2, something needs to produce CO2. So we need to have a balance. And in the closed systems, and Earth is basically closed system in general, we need to have this balance between we need to have balance between different species. So if we have a monoculture, it's harming the soil and it's harming the nearby environment. And lately, in May last year, there was a publication in Nature Communication about how biodiversity loss reduces global terrestrial carbon storage. So I encourage you to read it or give it to students. So if you have rather people with theoretical approach, why not? If you have people, ambitious people with a practical approach, let's ask them to build a minimal ecosystem. So the one that won't end after hour because it's drained of the fuel, or because the concentration of the metabolite is toxic and the life ends, but with carefully composed structure of this ecosystem with producers, consumers, and decomposers, we can have a sealed jar that lasts for years. And theoretically, infinitely, just there is a energy coming from the sun that powers the photosynthesis, but carbon inside, water inside, nutrition inside are kept in the loop, being consumed and decomposed. It's not a trivial task, but it's beautiful to create a thing like this. And again, it's not a new concept to build a garden in the jar. What we think it's new is to build the to qualitatively assess what's happening inside the jar, while the balance is going to be obtained, because you will see initially that there will be a lot of fluctuations in a lot of different parameters before the balance will be reached. But so far I focused just on CO2 because it's the detector that it's good for start, because it gives you a lot of options for a lot of different measurements with the affordable price. But then there is a question if we can do anything more. And yes, of course, we can. Oh, sorry, in no way pictures disappear. I'm sorry for this, but what we can do. Um, okay, sorry, pictures disappeared from the presentation. Okay, but still. Sorry, PowerPoint cracked. fortunately, at the very end, not now. Okay. Yeah. So the next, what would be here? The next step. Uh, Use different gas detectors. So use, for example, detectors that I showed you in the beginning. The one that measures methane, the one that measures ammonia, the ones that will show us something different. I have here also a very cheap light detector. So if we have both CO2 detector and light detector, we can see the correlation if we have a green plants performing photosynthesis about how the intensity of the light relates to the capture of CO2. We can as well do other things with other gases. And we can also check how the presence of oxygen influences, for example, how the compost behaves. Because again, we all know that the compost is there and the compost is getting warmer. But when we actually stick a thermometer in this stinky mold of rotten food, we can observe something interesting and simply check what's exactly happening inside, and again try to control the process. So check what if we can detect, for example, methane if it's anaerobic, or CO2 if it's aerobic, and so on and so on and so on. So here is the place where I end my presentation, which was to inspire you that with modern electronics, even without um, any skills in programming, you can do a lot on physics, chemistry, biology, or any other subject. So you can do qualitative studies of very interesting systems, biological systems, that raises the awareness simply of how the environment works. Okay, so that's it from me as the introduction to this scenario. Now, as the presentation ended, I'm checking what happened in the chat. Okay, or if you wish, you can go to Q&A or simply turn on the camera if you wish. If you have any questions. I see one. What water gives high electrical conductivity? So the hard water, for example, again, distilled water has very low conductivity, but like mineral water, yeah, it's called mineral because of the amount of minerals that are inside. So again, if one can quantify, checking how many minerals are actually inside, and compare it with the results. So how this influence the plant. But again, if you see that, for example, you have too high electrical conductivity of your soil, just add the distilled water or demineralized water. Is it possible to use Roundup to show if it kills biodiversity? That's a bit complicated because Roundup, uh, I, um, I wouldn't say it kills biodiversity. I mean, it's a complicated issue of like with antibiotics. We need to use them for a particular purpose. When it's overused, it's a problematic. But as far as I'm concerned, the use of Roundup is quite specific. I mean, it kills what it's supposed to kill if used in appropriate amounts, while still not being as aggressive as other herbicides. Okay, are there any questions or comments? Oh no, that was my hand. Again, feel free to simply write on a chat or turn on camera or whatever you wish. I will count to 10 and then end. Okay, I don't see more. Or I will stop the recording if this is the case. So in case if it wasn't the case, thank you very much for your presence. And all the recordings will be uploaded to our YouTube. So I will send you the information when this is done. And I hope you don't mind me sending you during the autumn the summary of the refined version of our scenarios, so you can use it in your classroom, hopefully. So hopefully, let's stay in touch and goodbye.